Hello guys, today we will implement the disjoint-set data structure. I assume that you already know about this data structure. If you don't know about it, please read about it. I provide a link in the description. But today I will start from the implementation. And of course we will do this implementation in Haskell. So I will try to be as abstract as possible, and that's why I will start my implementation by implementing the type class for this data structure, which provide to us all the methods which provide the interface of this abstract data type. So I will call this type class is like disjoint-set, okay? And it has some type C, abstract type, and we need to define some methods. So the first method is the empty, which built for us our container type, which contains some elements of type A. So A type is actually the type of our elements. And because we comparing our elements, I need to provide port constraint here. Okay. And let's go to second function. I will call it makeSet. This function takes some element of type A, some container of which contain the elements of type A, and produce a new container. Of course, we also need the ordering type class here, and I will put it. So the next method is find. The find method is taking some element, take some container which contain our disjoint set, and it return to us. Maybe it return to us the representer, the thing which represent our connection component in which this element presents. So, and because we can have no element in our disjoint set, that's why we need to use maybe here. And the second thing, I will also return some integer. So I will return the representer as a pair of the representer element and the integer. The integer is the number of the elements in this connection component. Okay. And now let's define last function. This function I will call it union. It's take two elements and connect the connection components to which they belongs. And of course it takes some disjoint set container and maybe. So I will use maybe here because we can be in the case then there is no elements at all in our disjoint set, and that's in that way we can't do any merging of the components. But if all the elements, the first element of type A and the second element of type A is represented in our disjoint set, then we possibly can do the connection, the merging. And the fact that they can do this, I will represent as a boolean, as the first value of the pair. This will be the fact that they actually do the connection, the merging. And the second element will be our new connection a new disjoint set. There are these two connection components connected. Okay, but if they not need to be connected, if they have the cycle here, then they just return the previous disjoint set, and we mark this situation in our first value as false. Okay. Now, when the done type class, we can implement the data structure which will do the implementation of this type class. So I will name this data structure as disjoint-set. It's a polymorphic type which takes some parameter, and we will define it as a mapping. So we need to use mapping, which at the case it has the vertices, and at the value it has also vertices, the parents of the of our vertex, which the vertex, the actual vertex, they put in the key, and the corresponding parent they put in the value of our map. And also in the value of our map, we actually put the pair where they have the vertex and the number of childs of this. So the childs in the subtree, the number of vertices in the subtree. So we represent our connection component as a trees. So the case, our type A, and the values in the pair that have our type A and some integer, which represent the number of elements in the subtree. And let's deriving show for us, so we can print our disjoint-set data structure. Okay. And from here we can go to the implementation of this type class for this data type. So we need to define the instance of disjoint-set type class for our data type disjoint-set. Okay, we'll start from empty. Empty constructor, which actually construct the empty disjoint set for us. So of course we construct it with our disjoint set constructor, and they need to provide the empty mapping for it. Okay. After this we can implement the make set function, which takes some element. It takes some container. This container represented as a map, and the end pattern matched here. And now we need to do a new mapping. So actually here we do the connection of this element to its parent, and because this is a new element, this is the first element of some connection component, it has no parents, and this situation we will implement as it is a parent of itself. So we take the insertion function of mapping and put as a key our vertex, and as a parent we put the vertex itself and the number of elements in this tree which it represents. And because the start to build our tree from only one element, the v itself, that's why it has only one element, and they provide it in this pair. And of course we do this insertion in our map, and this expression leads us to a new mapping. There they have this one only 1k, and we need to wrap it into our data type. So I think like this. Okay, now let's go to find function implementation. The find function takes some element. This is a current element at which we start to look in our tree, and of course it takes some disjoint set mapping. I will unpattern match it and also mark it at all as a D. Okay. First of all, when they have this current element, we need to this function will return to us the representative of connection component to which the core element belongs. So the first thing they need to do is to take the parent of this core element, and they can do this with lookup function, which search for the k in our mapping. And if this k in our mapping, then we will receive the just value. And this means to us that they in the maybe monad, and they can extract the value from this monad, and this value will be the pair. So this will be this pair where they represent the actually the element itself and the number of elements in the connection component. Actually, this is the number of the elements which in the all subtree of this element. In all the tree, this element represents the root, some root of the tree, and the I is the number of all the elements in this tree. Okay, then they have this pair. Then they can check what if this element is equal to our current element. This means that they in the root of this tree, and the root is the representative. This means that they can return it. But otherwise we need to find our representative again of this element D, and for our disjoint-set data structure. Okay. Pair, of course, pair, this is this pair, and they can name it here. And I think this this thing will work. Okay. Let's go to the next function. Now we can implement the union function. The union function take the two elements. Also, we take the disjoint set of course data structure, in which we want to implement the merging. If the elements present, we can try to merge if there is no cycle already in these two connection components. Because the return maybe here. This tells us that in the maybe monad, and we can use do notation here to define our monad. And the next thing we need to do, we can at first try to find our connection component representers of A and B, and for this we have this function already, which define to us these representers. So I can run this function for A, and I can extract this possibly can leads me to fail because find return a maybe. But if this accepts, we can on pattern match our pair A, and it has some A representer and A count. So the number of elements which belongs to this connection component, which AR represent. Okay, and also we can do the same thing for our B, but we name this as B representer, B count, and of course we need to call this for B. Okay, and from here we go to condition. Actually, they can at this point they can check if our representers are equal. If they equal, this means that we can do the connection. This the situation where we when we in the cycle, and I want to define this situation as I return the just, because all the elements A and B in our disjoint set, but we can do the connection. And as I said, I will mark this situation as false here, and I need to return our disjoint set as it is without any modification. Of course, otherwise I need to do the connection of this tree. I need to do merging or union, and actually here I will do the thing that called size union. So that's why we also counting for every node, we count the number of elements in its connected component. Okay, of course I need to at first return the just constructor, and then I need to provide a pair where I mark as true the situation that they need to do merging, that they do merging, and I need to provide some new disjoint set. And to define this new disjoint set, I need to provide representers with the number of elements in their connection components. And we already have this information here as AP and BP, and I pass these values into this function, which will define for me the new disjoint set value. Okay. How do I can define this new disjoint set? So actually we need to do merging here. How we do merging? We take the first connection component and the second connection component, look which of them have the maximum number of elements, and this is the maximum connection component. So we take the connection component that have the minimum number of elements, and change its parent to the parent of the connection component which have the maximum number of elements. And also we need to change because the connection component which have the maximum number of elements now becomes the new root for these two connection components, and they merge there. This tell us that the root of the maximum connection components now have the new count of the elements. It have the number of the minimum connection component elements plus the number of the maximum connection component elements. Okay, so let's start define this logic. As I said, they need to define new function nd which take a pair representer and b pair representer, and it's construct a new disjoint set for us. Okay, and they need to provide some new mapping, of course, and they need to define this new mapping. Okay, how can they define this new mapping? So actually we need to here provide some expression, and this expression presents new mapping, and this new mapping is done via two insertions. So we do two updations for our minimum representer and for our maximum representer. So we will use the insert function for this to change our initial mapping, and they change the values for minimum representer. They change it to new pair, which has as a first element maximum representer. This is a new root of the minimum connection component, and the number of elements will be the same. So this is the minimum number of elements in connection in minimum connection component, and they need to use here the some new mapping which I also need to define, and I will define it as exactly the same, but they need to modify the maximum representer, and of course the maximum representer node root node stay the same, and they only change the number of elements. The number of elements now is the sum of the elements of the two connection components. So actually they can use these values here, AC and BC, because some of them maximum and some of them minimum. Okay, and now I need only define the minimum number and minimum representer and maximum representer. And of course I can do this by using the max and min function, which take these pairs, A pair and B pair, and if I extract the maximum pair, I can define maximum representer here, and I don't need the number of the elements of the maximum connection component. And also I can use minimum here to define the minimum connection component. And here, of course, I need to define minimum representer and the number of the minimum connection component elements, because they're using it here. Okay. Okay, I think this should work. Yes. We can we can try to compile this thing. So I will load my GHCI and load file. Of course, I think will be some errors, and let's try to fix them. Variable not in scope BC. Okay. Of course, this variable not in scope. Let's use max. Let's define its number of components of the connection component as max n. And here we will use not AC and BC because they're not visible. We here in some nested scope, and we need to use these numbers here. And let's try to recompile. Okay. So these errors here, I think I need to add orderings, as the compiler said to me. So here they need to use orderings constraint, and let's try to recompile, and we're done. Okay, it's compiled, and actually I think it should work. Let's try. For example, I can now try to make some sets, so I can use function make set and provide some vertices of my set. Okay, some elements. Let's make a set for some, for example, A vertex, and they need to provide some empty container, our disjoint set with the empty function, and this will give to us the some value of our disjoint set. And of course we need to define type, and it will be disjoint set of char here. So we can run this, and we can see that we have this disjoint set here, and it's represented the map, and now it has only one element which maps to itself, and it has the counter 1 because this tree, this connected component tree is exists only from one element. This is a element. Of course, we can now using this set, we can create another set, another connected component. For example, we can add B here. Okay, and you can see that now we have a map which contains two connected components. Okay. And I think now I can write some helper function which takes some list of elements and provide a disjoint set which created from this list of elements. So we will add elements one by one from this list. I will call this function from list, and I don't want to write its type signature. I think Haskell can derive its type signature for me. I will receive on input some list, and I can use folder function. So folder with combination of a make set function. So make set function here, and I need to provide empty set. Okay, and they need to provide our list. Let's reload, and now I can try. Let's see its type signature, derive its type signature. You can see that our function takes some foldable T, which contains some elements of type A, and they produce some container type which contains our A's elements, and this type must be constrained by disjoint subset type class. Okay, now let's try to run this. We'll run this for list, for example, A, B, C, D. Oops, and you can see here I need to provide actual type for this expression. Okay, and our type is disjoint-set type with char. Okay, and now our set is created. Okay, let's save this set for here, and now I can try to use union function to connect some connection components. Okay, and let's look at our union function type signature. You can see that it's have some type which have this is a complex type. At first they identify that our vertices in our disjoint set that maybe, and then they determine the fact that they connected our components or not with the bool value. Okay, and first of all, let's write some helper function. I will simplify type signature for it, but I sacrifice the totality of the function and make this function Bartel function. I will call this function dunion. And it will take some vertex A, some vertex B, and some disjoint set data structure. And then I need to try to do union on A, B with on our disjoint set D. Of course, and here I have the maybe type. This means that I need to extract the value from just function and take the second element, because our second element contains our new disjoint set, which possibly can be done with connection of these two components of A and B. Of course, if this can't be done, our function will fail if one of the vertices A and B are not present in our disjoint set. And if we can't connect our components, then they just receive the same component. For example, here, okay, let's try to reload this, create our disjoint set again. Let's look at it, and now let's try to do dunion of A and C, for example. A and B. Let's connect A and B. So I need to provide A, I need to provide B, and our disjoint set. And you can see that our function hangs. This means that I do some errors in my implementation, and I need to fix them. And of course, the problem in such cases, the problem is here in somehow circle definitions. Of course, I need to at first I need to use our mapping, initial mapping here. This is our first mapping. The at first modify the maximum component, and then modify the minimum component in the modified component. Okay, and we build new component. So let's try to reload. Create our S again and run dunion. Okay, I run this dunion, and you can see that our A and B are connected now. At first, our A points to itself, which means that this is the rooted element with only one element, this shown here. But now our A maps to B, so it's like a tree structure. And this number shows that A has only one element. And our B, it also points to B. And here, this means that it is the root component. And here we have two, which say to us that this component, which represented by B, is now have two elements, two connected elements, A and B. Okay, and our C components stay the same. Of course, we can save this disjoint set like this S1, and now we can do the modifications in S1. So let's do some set, disjoint set 2, where the C and D connected also. And the initial set is set 1. Let's run this and let's look at S2. So you can see here that A and B connected, as in the first case. And now C and D also connected. Okay. And of course we can use this S2 to make a new connection component. Now we can connect this connection component with this connection component. For example, we can connect C and A. So let's do this and name our new component, new disjoint set as S3. We connect A with C, and let's look what will happen. And let's look at our S3. Here we have we connected A. The A representer was B. So we can see that here our B points to itself. But now we can see that it points to D, and C also points to D. And D points to itself. So our D now the root, and you can see 4 here, which means that it has 4 elements in this connection component. And our B have 2. This means that it has A and B, and C have 1, which means that the subcomponents of C have only 1 element. Now we can see that our we do the connection of all the elements in our connection component. And what happens if we try to connect some more elements? So let's use our C3 and try to build new C4, S4, where we try to connect, for example, B and D, or B and C. Okay, let's try to connect it B and C. Now you can you must understand that these two elements in the same connected component. And if I run this, you can see that actually nothing is happening because this connection was rejected. And of course we can check this if we run our not the union function but our union function, which will return to us this complex type, and this type will contain the information about what our components was not connected. So let's run it. You can see here we have just false, and this false tell us that our components was not connected because they already in the same component. And actually this thing can be used to detect a cycle in a graph, or it also can be used in a Haskell algorithm. Okay. So guys, I think that's all for today. In the next videos, I think we can implement the detection of the cycle in a graph, or to improve our Haskell algorithm with this data structure. Thanks for watching. Push like button, push subscribe button, write comments, and see you in the next videos. Bye bye.